So thank the organizers for this wonderful week that has been fascinating so far, and happy birthday, Jarko. So I'm going to talk about embeddings in multidimensional subshifts and the new property. So let me just briefly describe what is my plan and what is the purpose of my talk. So mainly to describe a new embedding theorem. If there's time, and probably there's not, I'll also talk about factoring. And there's kind of a dual purpose. The other thing is to kind of introduce a very simple concept which is used abundantly in other parts in mathematics, and turned out to be quite natural, in my opinion, in the context of symbolic dynamics. This is the context of retraction. And in relation to this, I would like to talk about a class of multidimensional subshifts, which seems natural to me. And this is the class of subshifts satisfying the map extension property. It's somehow related to this notion of retraction, closely related. And so these are the two goals of my talk. And I should say, and this is coincidental, that somehow, okay, the content of this talk can be found, some preprint preliminary version can be found on archive in a reprint of mine. Soon after this talk, I learned that, in Finland, the Jarko community, and also in France, they've been considering for the last 300 years also something related, and it's been introduced recently, and there are some fruitful relations. So keep in mind that you want to look at this if you're interested. Okay, very briefly, subshifts of finite type, the usual slide. I'm introducing this mostly for the specific context and notation. So a subshift is closed with respect to the product topology gamma invariant set of the functions from a finite set to your group. I will be talking about subshifts over countable abelian groups, always abelian in this talk. Some results make sense for more, but you should not consider them. And you can think about ZD, but as you've seen in earlier talks, even if you're interested in things about the integer lattices, ZD, sometimes you're forced somehow to consider slightly more general, like for instance, more general finitely generated abelian groups, and then you get for free this more usual. So you can think about ZD. At certain times you will have to, we will be forced to consider something a little more. And the subshift of finite type, okay, it's something where it's defined by a finite set of forbidden patterns. So W is like the window you're looking at, and whenever you slide this window, you don't see something from a finite forbidden set of patterns. And this is mainly for notations. For given a finite subset of the group, LF of X is the set of admissible F-shaped patterns. Okay, that's just notation. Okay, so this is kind of the usual slide just for notation. Now, the talk and the result are around the kind of concepts which I think are the most basic concepts of symbolic dynamics when considered from a kind of an abstract point of view, as a category, if you want. So in topology, the objects are topological spaces, and the morphisms, the maps, are continuous functions. In symbolic dynamics, the objects are subshifts, and the maps, or morphisms, they are shift commuting equivariant maps. So in practice, this means something given by like a generalized cellular automata in a sense, or like a sliding block code. By the Curtis-Hedlund-Linden theorem, a map is actually something which is given by finite piece of data. It's like you're given a window, you look to define an equivariant map from one subshift to another. You just need to know, given a configuration in a finite window, what will be the value at the identity, and then you slide it around. So these are finite objects. And then there are special maps, like an embedding is an injective map. So we say X embeds in Y if there is a map, which means equivariant continuous function from X to Y. Okay, so this is a special kind of map, and as Jarko showed, it's it's impossible unless you are in Z or something to know if something is injective or not. But okay, there are things that are injective. And a factor map, this is the commonly used term, is a surjective map. That's the term, and we say Y is a factor of X if there exists a surjective equivariant map from X to Y. And a topological conjugacy or an isomorphism is a bijective map. Okay, so from the point of view of symbolic dynamics, two subshifts that are topologically conjugate or isomorphic are the same thing. Okay, so it tells you, it captures some information, doesn't capture some other auxiliary information which might be relevant to you, like if it's represented by connected tiles, or if it's or the number of tiles, or other questions which are geometric or computational, or might have significance for your application. We're ignoring this part, or the purely symbolic dynamic point of view, or topological dynamic ignores this. So these are kind of the fundamentals of symbolic dynamics from the point of view of topological dynamics, from a certain point of view. And the questions which are fundamental from this point of view are, what can you say are when two subshifts isomorphic, when does one embed into the other, when does one factor onto the other? Okay, it's kind of the fundamentals, the starting point. And let me, for background mostly and for context, tell you what is the situation or part of the situation for the classical case of Z subshifts. So if you're talking about Z subshifts of finite type, and subshifts of finite type are again kind of not the only thing, there are many very important subshifts that are not of finite type, but they're a basic building block. And within them you have the topologically mixing subshifts of finite type. So to be topologically mixing, it means that whenever you have two admissible patterns, you put them far enough away, you have one point which interpolates them, which has this pattern here and this pattern there. And for Z subshifts of finite types, mixing are kind of a basic building block in the sense that any subshift of finite type decomposes into irreducible components and wandering points, which kind of, on first hand, are less important for the dynamics, and an irreducible one, if you pass to a power, becomes mixing. So somehow they're basic building block. Even in Z subshift of finite type, there are some, there are certainly unsolved problems. The isomorphism problem is, I think, the kind of the most difficult and unapproachable one somehow. Okay, and I'm not going to say much about that. But kind of keep that in mind as a warning that if you're arrive to the point where you have to solve this, then you have to be very, very ambitious, or say, okay, let's leave that aside. Okay, and but if you want to, so this is the question of when are two subshifts of finite type isomorphic. If you want to say when one embeds into the other, then there is an important theorem which I'll state in a moment and discuss further, which is Krieger's embedding theorem. Brian has already mentioned it, and it is a fundamental theorem in many ways. And it essentially resolves the problem. That's what I'll say. Essentially resolves it up to when you arrive to the difficult case of isomorphism. And there is a corresponding theorem about factoring. There are two theorems. I'll just discuss one of them. The situation there somehow is even closer to being resolved. One is there are two factor theorems by Mike Boyle, and they tell you when, at least topologically mixing subshifts of finite type factor onto each other. Okay, so this is Wolfgang Krieger and Mike Boyle, for those of you who don't know, and more importantly, for those of you who do know. And so within these theorems, I will have to discuss some concept of topological entropy. This is some numerical quantity associated to a subshift. And essentially, remember, so Fn, you should think about if your group gamma is like ZD, then you can think about it as a box of side length n. So this measures the number of patterns, the number of admissible patterns in a box, suitably normalized. Okay, it's a very basic concept. It's measuring, into some sense, how complex your subshift is. And so if you've seen, it's a very fundamental theorem, quantity, and it has a much more general context in topological dynamics, etc. But the definition here is relatively simple. If it's the first time you've seen it, okay, it takes some time to assimilate, but for most of you, it's probably not. And for convention, I will, just to save some problem, I will say that the topological entropy of the empty set is minus infinity. It's like, and the things you need to know about it for the purpose of this talk is that if X embeds into Y, this makes sense, right, according to the intuition, then it should have at most the entropy of Y. And if it factors onto the Y, then it should have at least the entropy of Y. Okay, at least this is in the same context of amenable groups, and we're certainly within this context for the purpose of this talk. Okay. So Krieger's theorem that I mentioned earlier, let me state it and say what it says now. So it says if you're given an arbitrary Z subshift and a topologically mixing Z subshift of finite type, and you want to know if X embeds into Y. So this is telling you exactly when this happens. There are two possibilities. One possibility is that X is topologically conjugate to Y. Then it certainly embeds because they're the same. I'm putting this in red because to actually know, say, if X is a subshift of finite type, if this is the case, okay, that's beyond us. But, that's one case. The other case is that X has strictly lower entropy than Y, and you look at the number of periodic points of period n in X, it does not exceed the number of periodic points of period n in Y. And if you think about it, it's quite clear that any embedding of X into Y will embed periodic points of period n in X into periodic points in period n in Y, so this is clearly necessary. The entropy condition, okay, with strict inequality is clearly necessary, and there is a relatively simple, well-known argument that says that if you properly embed into a mixing subshift of finite type, then you must have strictly lower entropy. Okay, so this is what it says. And now if you're kind of seen entropy for the first time and not really care about it and don't remember what the definition, so what does this say in simple words? Okay, it says that the obvious necessary conditions are sufficient, that's the important one, and one way to say it, another says, it says except for the case of, for the equal entropy case, it says that if it topologically embeds, if it embeds through a sliding block code, right, then it's the same as to say is just that there's a sum function which is equivariant and injective from X to Y. Okay, so forgetting about the topology, and this still mentions somehow the restriction about entropy to have some statement that does not mention entropy at all out of this. You can say if X properly topologically embeds, means okay, strictly embeds, not equal, then it's the same as to say is that there's a Borel function which is equivariant from Borel injective embedding, for which the image is not dense. Okay, so some way to concisely express the fact that It's saying the obvious conditions the obvious necessary conditions are sufficient. So this is the one-dimensional case. Now, years later, it was the question, what about multi-dimensional subshifts? And they are already much more complicated, as you have seen from the general talks. The general class of mixing subshifts of finite type is quite wild. There's some pathological and crazy stuff going on there. And the theorem is not true, and nothing of this kind, you know, a real expression will not look like this. And it's quite, you know, should not be expected that you get something for the general class. So you have to restrict to some extra conditions on your target subshift. And Sam Lightwood, who was Mike Boyle's student, considered this problem. And he had, as part of his thesis, kind of two rather long papers where he extended some part of Krieger's embedding theorem into higher dimensions. And specifically, so some parts work in dimension greater than 2, but he proved that if you have a periodic subshift and you're trying to embed it in a Z2 subshift, like the full shift, for example, with a certain number of symbols, or another subshift which is sufficiently nice, and there's a definition here, and there are many definitions for various properties, and I will not define this definition. Like square filling mixing. It kind of means that it's stronger than topological mixing, some specific property that was introduced for the purpose of this paper, but it does cover many examples. Then the only clear obstruction, which is strictly lower entropy, you cannot have equal entropy and be periodic because these kind of subshifts have many periodic points. So you can, and if you're equal entropy and embed, you must be conjugate again. Then you know the clear necessary condition is sufficient. And by aperiodic here, I mean like strongly aperiodic, not that there's no finite orbit. I mean that the stabilizer of every point, no point has any non-trivial periodicity. This is the meaning. So that's, you know, a significant theorem. It covers many cases. There are many important, interesting aperiodic subshifts. But still, there are also many subshifts which are not aperiodic, and they're also significant. And you're not, you know, the class of subshift that you're considering as sources is not the same as what you're considering. It is disjoint somehow from the class that you're considering as target. And also, part of the beauty of Krieger's original theorem and the proof is somehow that it combines the periodic point restrictions with the entropy restriction in an intricate way. So this question remained. So, okay, as I said, it resolves it. And again, it can be expressed as a fact that in the aperiodic case, if you have a Borel non-dense embedding of an aperiodic subshift, then it's the same as you already have a topological embedding. And in Lightwood's paper, one of the things that has been described, okay, so the significant result is saying this is a step towards, you know, the complete generalization of Krieger's theorem, which will be carried on in subsequent work. So I will describe this subsequent work.
Mm-hmm. So in your previous slide, and even in the Z case,
so I will.
So in the Z case as well, you said that if you have a non-densely Borel embedding, then you have a topological embedding as well. So this is a okay. It follows because.
It follows because. Okay, I will just briefly say it. I did not explain, but the entropy restriction is not only an obstruction for topological embedding, it's somehow also an obstruction for Borel embedding. Let's briefly, let's not go into too many details about it at the moment. Okay. So, okay. So just to introduce some notation, a stabilizer of a point, generally when a group acts on a space, is the space of is the set of elements of the group which fix this element that you're acting on, or this element of the subshift. And it's clear, it's general fact that this is a subgroup. Now, if I have a subshift, or a group acting on a space more generally, I can in a subgroup, I can consider all the points stabilized by this subgroup. Oh, and you think about it for a moment, this is a closed set, and in the abelian case, or when your subgroup is normal, all groups are normal in abelian groups, all subgroups are normal, then this is a closed invariant set. So this is a subshift of X, X gamma bracket. And now I'll make, for convenience and to avoid kind of repeating it, a distinction between the case where gamma 0 is a finite index and an infinite index. In the finite index set, I will denote by X gamma naught without brackets the points whose stabilizer is exactly equal to gamma. It's like, so in the case of Z, like gamma 0 subgroups of Z are either a trivial subgroup or they're indexed by an integer, right? So this is the points that have a fixed period, not, whose least period is the same. So this is the point. So these are subshifts of a given subshift. And, if I look at the things stabilized by a certain subgroup, like in Z2, if I look at all the points that are stabilized by the vertical direction, then somehow the configurations I look at are one-dimensional. They descend to a subgroup of the quotient, and this is what he's saying. And I'm putting this hat to denote kind of the natural quotient, the natural gamma mod gamma 0 subshift that I'm looking at. And this is part of the reason why I'm not saying ZD all the time and talking about abelian groups, because if you look at the quotient of ZD, and somehow you will be forced to do it, you will have to look at things which have torsion. You will have to look at general finitely generated abelian groups. Okay, so this is the notation. And now let me state a particular case of the multidimensional embedding theorem. And I'm stating it, first of all, just to be a little more slow and concrete. So I want to say when you have a Z2 subshift and when it embeds in the full shift over a given alphabet in Z2. Okay, there's not. So there are two cases. I'll give an if and only if condition, it is similar to Krieger's. The first case is that it's topologically conjugate. Now, okay, I can't say when that happens, but it's the one case and I'm not addressing it. Even the one-dimensional case, I couldn't say it. Or if it embeds and it's not topologically conjugate, then it's obvious that it should have less entropy. And then there are extra conditions. So the first condition involves one periodic direction. It says I give you a primitive vector, okay, this means like a vector that you can complement to it's like the vector 1, 0, shifting 1 in the horizontal or the vertical direction. And every multiple of this vector, if I look at the things that are stabilized under this vector, and I project it into a subshift which is kind of essentially one-dimensional, then there are two options. It can be topologically conjugate to the corresponding essentially one-dimensional full shift. And here you see that we already have to consider subshifts over a group which is not exactly Z, but it's something more than Z. Or it has strictly less than entropy. But this is not sufficient. Now I have to consider more conditions. So this is the two-dimensional condition, the one-dimensional condition. And the zero-dimensional conditions are saying that for every two linearly independent vectors, if I look at the thing stabilized by them, so if you're in Z2 and you're stabilized by two linearly independent vector, it means you're really periodic, you have finite orbit. And there are finitely many. This is a finite set. X VW and Y VW, X VW and YVW are the points stabilized by both V and the periodic under V and periodic under W. So periodic in 2 dimensions, they have kind of a finite fundamental domain. It's a finite set. So this finite set has no more element than this finite set. Okay, so that's the description. And now, okay, so you got this. It's kind of a direct generalization of Krieger's theorem for the particular case where the target is the full shift. And now let me give the full formulation of the theorem.
So Tom, just one clarification.
I will repeat it.
Y bar, NB, and A, these to be conjugate as...
These are conjugate as
Z subshifts or
Z cross Z mod
Z
N
mod
Z
N
subshifts.
subshifts.
So, yes, to emphasize, the conjugacy here is over this virtually Z group. Okay, so the formulation of the full theorem says the following, and it's a little bit more concise but I wrote than what I had before, but it requires some explanation. So let gamma be a countable abelian group, and now you have two subshifts. X is arbitrary, it's two gamma subshifts. X is arbitrary, Y has a certain property which I'll define. This will be important, this will be the next thing, called the map extension property. Then X embeds into Y if and only if for every subgroup of Y, this covers all the cases, one of the two things hold. So either it's topologically the gamma zero periodic points in X as a gamma subshift, which is the same as to say, if I project it as a gamma mod gamma zero subshift, are conjugate to Y, gamma naught, as a gamma subshift or as a gamma mod gamma naught subshift. That I don't know how to check this, but I mean, it's mysterious. Or it has strictly lower entropy. Strictly lower entropy. Now, in the case where gamma zero is a finite index subgroup of gamma, I mean the projection, then a gamma mod gamma zero subshift is like a subshift over a finite group to say the entropy is just, you know, it's in one-to-one correspondence with the number of points in the subshift. Yes, Brian? That will be the next slide. So it's an important property that I will describe in a moment, but I'll say it's a property that it holds for the full shift, let's say, and for many examples. It does not mean this theorem holds. Okay, it's not a triviality. It's not a property that means the conditions of this theorem hold. So and you know, there's a slight more complication that was not seen that you can ignore for the case where you're trying to embed it to the full shift, which means that the subshift you're trying to embed, okay, when you restrict to the fixed point, they're no more degenerate than what you're trying to embed into. I'll say what this means. So the kernel of a subshift, or in general, the kernel of an action, is the set of elements of the group which act trivially on everything. So think about it. An obvious restriction is that, you know, if you're trying to embed like a Z cross 2Z subshift into another one, and the other one is, you know, invariant under the action of the involution, you know, what you're trying to embed is invariant under the action of the involution. You can only embed things which are invariant under the action of the involution. It's an obvious restriction. It seems a little stupid. It was stupid if you did it with the original subshift, because then you would actually be working in a smaller group, or in a quotient. But it can happen that your original action is faithful, but when you restrict to this x gamma zero, it happens. So you can encounter this trivial, stupid problem, even if it did not exist originally when you quotient by something. So it must be said. So this is the statement of the main theorem, except, okay, it's incomplete, as Brian has said, because I did not define yet what this property means. But let's say for the full shift, it makes sense. So the second and last part of the talk is to discuss this property and things related to it, and I think it's important. So the way I discovered it is kind of by doing this for the full shift and then trying to extend it in a way that it completely extends Krieger's theorem, and it does. You're restricted to the one-dimensional case. It covers all the mixing subshift of finite type. But somehow I discovered that it's an interesting class of subshifts by itself, not just for this theorem. So let me define it. So I'll introduce this notation of x squiggly arrow y, which means that whenever you have a point in x which is stabilized under something, then you have a point of y which is also stabilized under the same subgroup. And the meaning of this condition is this is a clear, obvious, required condition to have just a map from x into y, because every point in x has to go into something which is also stabilized by the same thing. It could be stabilized by something bigger, if not. Okay, if you have a fixed point in x and you map into something, the fixed point must go to a fixed point. So whatever you're mapping into must have a fixed point, etc. So the map extension property means that whenever you have, so y has the map extension property if the following holds. Whenever you have a partial map from something into y, and there are no obvious periodicity obstructions to have a map from x into y, then you can extend the partial map into a map. In particular, x0, x tilde here can be the empty set. Okay, so it means always when you have an x and there are no obvious periodicity obstructions, you can have a map from x into y. This is the definition. Now, okay, so that's what I said in words. In simple words, it says any partial map into y extends unless there are obvious restrictions. Now, to be completely honest, I will say the version in my paper, there's an extra requirement, which briefly means that, there are not too many obvious restrictions. Somehow y already has some periods, but as Ville very cleverly explained to me a couple of days ago, it turns out this automatically holds, for example, for finitely generated abelian groups. So another condition, it automatically holds. And now this condition, a lot of you might not like it. It seems very abstract and, okay, like some functorial thing. But I will say in a moment, I will convince you that, okay, you cannot check anything basically about multidimensional subshifts of finite type if they're given in terms of forbidden blocks. But this is a very concrete condition, and there is a concrete way to describe subshifts with this property that witnesses that they have this property. Okay, so not as forbidden blocks, there's a concrete, very simple way to tell you that the subshift has this property. You don't have to check, for every or something. Just something concrete happens. And this something involves the notion of a retraction map. So what is a retraction map? This is a very simple, basic, general concept from topology and other areas of mathematics. Yes?
So if the subshift has the map with the map extending property, does it imply that it is entropy minimal?
The question was, if a subshift has the map extension property, does it imply it is entropy minimal? I will not explain what entropy minimal is, but the answer is yes. It implies many good properties. It's a very strong property on one hand. On the other hand, it's not a void property. It doesn't hold just for the full shift. There are many examples for which it holds. And so this, what I think makes it an interesting class. So a retraction is just a map and the map in the context of subshift, I mean continuous equivariant, from a space to itself. They apply it twice, it's the same as applying it once. Okay, and a retract is the image of the retraction. So if you have y, a retract of y, also in topology, is the image under a retraction. So it's like, the one-dimensional circle is a retract of the sphere is a one-dimensional retract, is a retract of the ball minus a point, okay, in topology. That's And one point is a retract of any space, etc. And the nice thing is if you're a retract of something, you're both a subshift of it and a factor of it. Okay, to say you're simultaneously those things. So retractions, we consider embedding. Factors, retractions are somehow very natural objects and many properties pass to them. And, you know, they've not been discussed that much, but they're really out there, I think, with the fundamental types of maps. Now, there is a very classical old concept in topology called an absolute retract. So you have a topological space, it's an absolute retract for some class of topological spaces if whenever you embed in something from you're in this class, whenever you embed, you retract, you're a retract. So in the class of subshift, a subshift is an absolute retract if whenever it embeds in another subshift, it's a retract of that subshift. Sounds strange, but these exist, and there are many of them. And it turns out that for gamma subshifts being okay, so let me say, it implies strong properties, that's kind of clear. If you're an absolute retract, then you are topologically mixing subshift of finite type and much more stronger properties. And you have a fixed point. So having a fixed point, it's clear because all of these are kind of easy observations once you unravel the definitions, but kind of you have to observe them. A fixed point, you know, if you have a fixed point, and any retract must have a fixed point, because you know, any fixed point must map into something, it must be a fixed point. And you know, the mixing passes to factors, and the retract of a subshift of finite type, unlike a factor, has to be a subshift of finite type. It's a little exercise that I will not do here. In Z, it's exactly the same. So there's this there are many definitions of subshift of finite type, but to say you're a Z mixing subshift of finite type with a fixed point is the same as to say you're an absolute retract for the class of Z subshifts. For ZD, it's a much stronger property. Now, this fixed point is something I want to avoid. I want to characterize, let's say, mixing subshifts of finite type, not necessarily with a fixed point, so you tweak the definition a little bit. So I discussed already that Borsuk in the 1930s discussed absolute retracts for some class of spaces. So if I consider spaces, so I have some class of spaces which is closed under isomorphism and passing to subspaces and to closed subspaces, let's say. Then, then it turns out that the map extension property is the same as to say you're an absolute retract for some class of subshifts. Okay, if you have a fixed point, it's for all subshifts. If you don't have a fixed point, it's for the subshifts that don't have that you know, avoid the obstructions due to the fact that you are missing some fixed point, some periodicity points. That turns out to be the case. And so, for example, to check if you have a fixed point, to have the map extension property is the same as to say you're a retract of the full shift. And if you don't have a fixed point, then it's the same as to say you're a retract of some specific, natural, very concrete subshift that it's easy to check. So I can give you a block map, and there, you know, just as it's easy to check if you're, many things are difficult to check, but given a block map, let's say from the full shift, it is decidable and easy to check if it's a retraction. Because it's easy to check if two block maps define the same map. So, I mean, very few things are easy to check, but this is one of them in multidimensional. So you can have a concrete description that witnesses that some subshift has the map extension property. That's the take-home lesson from this. And then it has many, many kind of nice, desirable properties. So, okay, in these subshifts, map extension property characterizes mixing SFTs. It passes to, if you look at the quotients by fixed points, this property, persists. And it guarantees that you have many periodic points in many ways that I will not fully say, but for example, the periodic points kind of recover the entropy, and they are dense, and more than that, at least for the class of groups that I'm considering. And there are also many natural examples, some are obvious, some are less, that have it. For example, any subshift with a full shift, any subshift with a safe symbol. I will not go into details what says that. If you look at colorings of ZD, then if there are sufficiently many colors, then it has the map extension property. In Z2 it's 5. It's not 3 definitely, I don't know about 4. Yeah, this is a part of a more general phenomena. And just something I haven't worked out completely, but I think that if there's this model for random subshifts, and in some sense I think most subshifts have the map extension property, but this is not a proof. I'm writing it as a conjecture because I've not done this yet. And so just to conclude, say something about how this map extension property comes in. So it comes in various ways, but kind of a key idea of the proof, is that it's somehow inductive. You do it by induction on dimension, so you build the embedding bit by bit, and to do it, it's more convenient to generalize the theorem a little bit, and to say not only you can embed under these necessary conditions, but if you partially embedded, you embedded a subsystem, or maybe nothing, then you can continue this embedding as long as you left enough space, or you're guaranteed to be able to do it at every point. So this is kind of a formulation that is slightly more general even for Z subshift, but you should be careful about exactly what it says. It does not say, for example, that you can extend automorphisms somehow of periodic points. It does not touch this point. But it's slightly more general, and it's suitable for the structure of the proof and the inductive structure. Okay, I will not say, it's not really, there's not really time to give more ingredients about the proof. So I'll just conclude and say that I think the take-home lesson, one of them is that somehow the notion of retraction and closely related notions that Vila told me about homotopy maybe, or contractions, contractible subshifts are, I think, fundamental, fruitful, and worth studying further. Multi-dimensional subshifts with the map extension property, I think, are a good class of subshifts to look at. They have a good structure theory, and there's some more evidence that I have not talked about for that. And we have a full extension of Krieger's theorem to subshifts over countable abelian groups. There's more work to be done later. And that's it. I think I'll conclude there. I wrote down one of many open questions, and I'll finish here. Thank you very much. Thank you.
Any questions? So maybe I have a question. You said at some point that it was easy to check on multidimensional subshifts whether an embedding was an embedding at
whether the map is a retraction.
Whether the map is a retraction.
Yeah.
Do you suppose you already know the language at that point? Or?
Yeah. Okay. So let me say, it's easy to, if you have a map from the, let's say specifically from the full shift,
okay.
Then it's easy to check if it's a retraction. If you have a map and the language, okay, you can check the language, then it's easy. That's all I'm saying.
Okay.
That's of course, yeah. But for the to be an absolute retract, you must be a retract of some very simple subshift, which has some very, if in the case you have a fixed point, then it's the full shift. If the case not, that it's something that the restrictions are you don't have points of certain periodicity. This is very simple, and you can check the language.
Okay. Yes.
Have you checked your question in the case of the free group?
So first of all, I've not. I mean, this is where I am at the moment. For the free group, okay, it's on one hand much more complicated for group theoretic reasons. There are many more subgroups of the group, and some things change. It's not a billion, subgroups are not. It's also more complicated because entropy is Sophic entropy, and some things are wrong for it. On the other hand, from other aspects, subshifts of the free group are simpler. So the answer is, I don't know. I think it's a slightly different sort of problem.
If you have a retract, can you say anything about what happened under the automorphism group of the larger shift?
Okay, so I thought about some things, but I don't know to pull something too intelligent. But it seems reasonable. A lot of things behave nicely. Like cohomology, for example, behaves nicely under retractions.
Do you know any strongly reducible subshift which does not have the map extension property?
Yes. So there are various arguments for that. I think Willy has a different one. But one nice, let's say, way to show it, there's a kind of even stronger property called strong spatial mixing. It's slightly complicated but natural property, and stronger than strong mixing. And Raimundo has shown me an example of a Z2 subshift, which has this strong spatial mixing property. But when you restrict to the points that are periodic under one direction, under shifting vertically, let's say, the one-dimensional subshift you get is not topologically mixing. And this contradicts having this property.
Could you please explain again how to get rid of the fixed point condition?
So the fixed point condition, you get rid of it by saying that you're not an absolute retract for all the subshifts, but let's say you don't have a fixed point and you don't have a point which is a stabilizer under a certain small subgroup, but other than that there are no obstructions. So you consider all the subshifts which don't have a fixed point and don't have a point with stabilizer equal to some specific subgroup or containing some fixed subgroup, and then you're absolute for them. And it turns out to be equivalent to being a retract of one specific subshift, or there are many choices of subshift, which doesn't have these points. Okay, like you just, these are the restrictions you make. There's no point which is fixed, okay, it's not exactly, but you make some compact condition that forbids this.
So I have no questions per se, but Brian asked about the automorphism group. So I think on any finitely generated group, the map extension property implies that the automorphism group of a full shift on Z will embed just by the usual marker stuff and paths and conveyor belts and stuff. And then someone asked about what was this about? Yeah. So you mentioned this argument about the period troubles for strong irreducibility versus map extension, so you can come up with this. So this generalizes to all groups, I think, which are not just infinite. So you can, to a large class of groups will have that property. So and then for the last thing, I wanted to just point out that you mentioned that also in these higher dimensions we have the same problem, that the isomorphism problem cannot be solved, but just to channel, I don't know, Emmanuel Chandel and maybe Pascal Vanier and perhaps also the community, in some sense this is an easier problem, because in one dimension it's a mystery. We don't know if it's decidable. We don't know how to solve it, and we have a lot of partial things. In 2 dimensions, we have a complete solution. It is undecidable. It is sigma 0, 1 complete.
Right.
So in some sense, it is even worse, but in some sense, it is nicer. So, okay.
Yeah. In 1 dimension, you know, we say maybe we're just too stupid and it can be solved, but in 2 dimension, we know there's no hope. Okay.
Any other questions? Let's thank Tom again.